I'm Leah Cheshier, NASA Public Affairs Officer. We're excited to be with you today to discuss the International Space Station and beyond as we celebrate 20 years of continuous human presence on the station. So for the last 20 years, this unique microgravity laboratory has hosted more than 240 people from over 19 countries and over 3,000 experiments and a variety of international and commercial spacecraft. This all helps pave the way for NASA's human lunar exploration plans under the Artemis program. This will call for us to send the first woman and the next man to the surface of the moon by 2024 and establish a sustainable exploration by the end of the decade. So we have 4 panelists with us today to share their wisdom and experience about all things space station. And I'm going to let them tell you a little bit more about themselves. First up, we'll start off with Robyn Gatens.
Hi, everyone, and thanks for tuning in. We're excited to be joining you today in this panel. I'm Robyn Gatens, and I have worked for NASA for 35 years, pretty much my whole career. I currently wear 2 hats for the agency. I'm the acting director for the International Space Station at NASA headquarters, and I'm also what's called the system capability leader for habitation systems. That includes environmental control and life support and crew health and performance systems, which we're using, we'll talk a lot more about in this panel. We're using the space station heavily to develop those capabilities. So that's it. That's me, Leah.
Thanks so much. And next up, Jennifer Fogarty.
Hi, it's a pleasure to be here and an honor to be on the panel. I am the Chief Scientist for the NASA Human Research Program. I have been with NASA 16 years in total, spent my career working most of it in medical operations, trying to understand the risks associated with spaceflight and making sure that the crew members are healthy and have the countermeasures they need to be successful for mission requirements. When I moved over to the Human Research Program, I became in charge of a very large and diverse portfolio of research that's trying to enable human spaceflight exploration. And we use platforms such as the International Space Station to not only understand how the body changes over time and how humans respond to spaceflight, but then how do the tools that we introduce, like exercise countermeasures or nutritional countermeasures, help them really optimize their performance and health and sustainably be able to manage the stressors that are going to occur for exploration missions, which we have not experienced yet.
Thank you so much. And to round out our panel today, we have Laura Shaw.
Hello. As you said, I'm Laura Shaw. I work in the International Space Station Program Office at NASA Johnson Space Center in Houston. I've spent my whole career working ECLS, life support systems, environmental control and life support. And so now we're establishing a test bed on board the International Space Station, as Robyn mentioned, to test out those technologies. And so we'll talk a little bit about my role in that, which is to create this test bed and all the hardware that goes into it. And I've been at NASA about 22 years or so and worked life support almost that entire time.
Awesome. Well, thank you all so much for joining us. Without further ado, let's dive into some questions. The first one is for you, Robyn. You've said before that the best is yet to come, and we're on the cusp of some huge payoffs from our investment in the International Space Station. So can you elaborate on that?
Yeah, absolutely. We've been talking a lot about this anniversary that we're celebrating, 20 years of continuous human presence on the International Space Station, which is just an amazing accomplishment all by itself. Our team makes it look easy, but in fact, it's not to sustain the International Space Station and continuous crew. But as we look back on that amazing accomplishment in the last 2 decades, we're really looking forward. We're looking forward to what the next decade holds for the International Space Station. And in all of our mission areas, I feel like we've already accomplished so much, but the best really is yet to come. So we'll be talking more today, and the focus of this panel is on how we're using it, the space station, for exploration. And we have all these capabilities that require the International Space Station as a test bed to close these gaps for future missions. So we're going to be closing gaps coming up. We're also going to be doing more cutting edge research in medical fields, manufacturing, all kinds of, for benefit to life here on Earth, STEM activities, all of those. The international partnership by itself is, I think, as you mentioned, we have all these countries participating. We're up to 108 countries have participated in some way in activities on the International Space Station. And so we're filling in the map, right, of global participation in this amazing platform. We're also seeing more countries want to send astronauts into space. And then our final area, commercialization. So we're trying to enable a commercial economy in low Earth orbit. We're opening up the space station for private astronauts to come for the first time, and all commercial activities. We've got 21 commercial facilities now on the International Space Station, owned and operated by private industry. We're about to launch the NanoRacks airlock on SpaceX 21, adding yet another commercial capability. So that's why I say, I think the best is yet to come. We're about to really reap the benefits of, in all of these mission areas from the International Space Station.
That's really exciting, and thank you so much. The next question is really for any of you, maybe even all three of you. How are we currently using the space station to enable future exploration?
Jen, you want to take that one first?
Sure. Yeah, it's been an exciting opportunity several years ago when they completed station from a construction standpoint. But as you heard from Robyn, it's still going to continue to evolve and change as a test bed. But we also were able to get enough crew up there where we could focus significantly on science. And one of the components of science, not the only, but one of the components is human research, to really characterize what happens with the human body over time. Spaceflight has some stressors associated with it, but it also has some absence of stress. So one of the big ones we try to understand is the body not experiencing gravity for significant periods of time. And the human body we've discovered is incredibly adaptable, but we're trying to understand where does that adaptation take you for periods of time that are longer and longer than what we experience on station. So you use something like station and the powers of the national lab that are there, plus the up and down mass, the capability to bring samples down, send hardware up and bring samples down to do more detailed studies over time. It's called time course. Because what's important about looking at change over time is your ability then to predict for future time periods that haven't occurred yet and build that confidence that you know where the system is going. So I think the station has just been remarkable with allowing us to look at multiple crew members at a time, men and women, people of different ethnicities, to really get a comprehensive sense of what people of the future might be looking at and how would we help them survive, and not just survive, but really perform to the mission standards that we expect for something like a 3 years Mars mission. So it's one of our many analogs, but it's our most high fidelity analog because it is space operations.
All right. Coming up next, we actually have a question. I think this one might be for you, Dr. Fogarty. What have we learned from human research on the space station that is preparing us for the missions to the moon and Mars?
Well, for the missions of the future coming up in the near term, especially for the moon, I think it was allowing us really to position ourselves to learn how to do human subject research in a very constrained environment. There's also risks associated with doing research. So we're always balancing enabling the mission to occur and doing research on subjects. But we have to remember that it is field research. So when people are going to go into space and go to a planetary surface, understanding how they perform on something like an extravehicular activity is part of what we have to understand when they go even further away. So I think it's a learning opportunity for the scientists in just executing the science on those missions as much as it is the data that's going to come back. But the data really is invaluable. One of the questions we have about microgravity, which is primarily the situation on the International Space Station, is the body I call it like one of the most energy efficient machines known to man, in terms of it will stop investing in systems that you don't regularly use. So I think what's probably pretty well known about spaceflight is you do lose some bone and muscle mass while you're in spaceflight because your body doesn't feel the pull of gravity. So your body doesn't invest in it. And it's not very hard work physically to live in microgravity, right? You don't have to, there's no weight to things. There's mass, but you're not lifting your own body, or you're not lifting an object. You're kind of just moving it around and making sure it doesn't get away from you. But it's technically not very demanding on the musculoskeletal system. So you say over time, we're going to take people to a planetary surface. So in the concept of the lunar orbiting capability, we're going to go to the lunar surface, which has a partial gravity. So the question has been, what value is going to a planetary surface from the human standpoint of getting exposed to some level of gravity that's not quite what we experience here on Earth? And we have ways on Earth of modifying centrifuges and putting people in an analog situation, which is called bed rest, to decondition them. But we're always concerned, like, how much do we really replicate the actual experience of spaceflight? So these opportunities of using combinations of learning about how microgravity changes the body, but then when we go to lunar, how does that compare, and how long do they stay in lunar orbit in microgravity? And then when they go to the surface. So there's a lot of, call it like triangulation of the data to look at, do we see differences in how the people decondition or not when you have a partial gravity capability present? So that's where we try to tie in what we do on Earth, what we do in low Earth orbit, and then what we're going to do in lunar, and make sure we're always evaluating the data to say, and I think Robyn used the word gap earlier, what are our gaps in knowledge? And then where do we actually know we have problems that we have to go solve and test solutions? So there's just different kind of approaches along the way, but we really have to make sure that it's an evidence-based process, and we're always reevaluating the data to tell us where to go next.
Fantastic. And so let's switch gears a little bit. We've been talking about the human side, and let's talk a little bit about the environmental control side. So we know environmental control and life support are essential for all human spacecraft. And on the space station, we have the ECLSS, or Environmental Control and Life Support System. That's our acronym for our big, long string of words. So how has that evolved in the last 20 years, and how will we apply the knowledge we've gained from that to those future missions to the moon and eventually Mars?
And I can take this question. When ISS first began, we first had astronauts on board 20 years ago. We had a very basic ecosystem. For example, we had a pressurized atmosphere, obviously, for the crew to breathe. And we removed carbon dioxide, but we brought up oxygen in tanks. We brought up water in bags, or we transferred it from the space shuttle. So we were in that state until about 2008. And that's the point where we brought up our what we call regenerative ecosystems. And these are the recycling systems. So we started collecting crew's urine and converting that into drinking water. We started generating oxygen from that water. So we no longer had to bring these really heavy consumables from the ground. And that's saved millions of pounds of up mass, we call it, to the ISS. So we've not only have we saved that up mass, we've learned a lot about these systems. And some of it's been painful, some of it's been very challenging, because these systems are all connected. When, let's say, we have a little contaminant that comes through the water system, that's going to go into the oxygen generator, and that's going to potentially negatively affect it. So we've learned about these interactions between those systems. And also, Dr. Fogarty said it, the human's a little bit different in microgravity than they are on the ground. And we've learned about that as well, and what impacts that has to the ecosystems. For example, we talked about the muscle mass and the bone mass loss. That results in extra calcium being shed and entering the crew's urine. Well, that affects our systems. We learned a lot about that particular one really early on in our system tests. So we're taking all of the knowledge we've gotten over the last 12 years with these systems, really 20 years for the whole of the ecosystem, and we're applying them to upgrades, to evolving it to the next step to make things even better, either more capable of handling the environments that we'll be in, or more reliable. That's a big one, because the ecosystem requires a lot of consumables and spares, because things wear out, pumps wear out over time. So focusing on improved reliability is a significant part what we're trying to do. And ISS is an incredibly unique, and in fact, it's unique in our solar system, at least, as far as a test bed where we can combine the microgravity, obviously, is a key. We can combine that with the crew being exposed to that microgravity and the waste products that they give off, and the closed loop spacecraft environment where, if you're breathing out things, those are in the atmosphere and they're not going to you can't open the window and then flush them out. They're there and you have to deal with them. So what we're doing is we're creating this exploration class life support test bed on the ISS, where we're upgrading our existing systems and we're supplementing them with new systems that will close the loop, we call it. So, we've got this loop of carbon dioxide coming out, being recovered, the urine being recovered, and that water goes to the oxygen generator, et cetera. There's a loop there. We're closing that loop to make it where we don't need as many consumables as we've needed on ISS. And that's only going to help us for a Mars round trip mission. So it's very exciting, and it's a one-of-a-kind opportunity that we're really taking advantage of.
Yeah, absolutely. The best place to test it is in space. And I think it's very interesting. I didn't know that we were still sending up water up until 2008. That's very interesting.
Yeah, we still send water today. We get about 90% of our water recycled right now. We're hoping to get to 98, 99% with our upgrades that we're currently working on.
Next year.
Next year, yep.
Next year, we're going to close that gap.
Yeah.
And I'll just add on to what Laura said, that water recycling system enabled us really to go from a crew of 3 to the crew of 6 and now 7 that we have on the International Space Station today, because of that we cut that resupply need in half. And what does that mean? That means more crew can do even more research. And so that's just had a huge payoff.
Yeah, absolutely. And more research means more benefits to humanity as well. So we know there are considered 5 hazards to human spaceflight. We're looking at radiation, isolation and confinement, the distance from Earth, gravity fields, and hostile or closed environments. So what are some of the countermeasures in place to combat these 5 hazards?
Yeah, and those hazards we do break down on a per risk basis, but I always remind folks, I mean, the human's going to experience those hazards pretty much simultaneously. The International Space Station does have all present to a degree, and we're trying to understand the difference between, say, the plan for exploration versus ISS to know what space we still have to work on. And there are modifications being made to ISS with that in mind, as well as the lunar opportunity. Well, right now, we use predominantly exercise for the microgravity, the altered gravity hazard, right? We got to reload the body in some way. We got to make it work hard. And going back to both Laura and Robyn's points, really when you think about the human in this loop, it's called human system integration. Like, how is the human going to affect the vehicle? How does the vehicle affect the human, and the cyclic nature of that? So if we can load the skeleton, we can make the bones and muscles work regularly and keep the body performance ready and healthy. And there is a psychological component to exercise as well as physical, but then maybe we're less of a burden on the urine recycling system. Can we kind of meter out how the calcium is lost? There's also the nutritional side. How do you feed a body and prepare for the waste that's produced when you feed a body that's exercising a lot? So we have to kind of understand all the inputs and outputs of both the human and the vehicle system to come up with a solution that says it works for everyone, and it's something that we think we can inform how future vehicles should be built. What did we learn from it? So I think that human system integration has really come a long way with understanding how we impact each other and maybe how we trade off what we need to do and the good solutions. The space radiation is interesting. We definitely get galactic cosmic rays, which is a very different type of radiation than we experience here on Earth. But we also have a looming hazard known as the sun that puts out some solar events. And those are solar particle events that we even experience here on Earth that make it through that protected part of our atmosphere called the magnetosphere. And those are all, significant potential health risks, right? I think It's scary, and it's pretty well known that radiation to a large extent is not your friend. It can be used therapeutically at time under very careful, guidance from physicians and scientists. But in general, it's something that we know really damages your body on very different levels, cellular levels, even genetic levels, like damage to DNA. So at this point, there is a level of shielding, actual aluminum that can come between the human and the radiation. Another thing that you can do is reconfigure, and I think Laura brought up the water bags. That can be an amazing radiation shield. So depending on the type of event, which are pretty rare, the crew can shelter in place and use physical stuff around them to protect them. Galactic cosmic rays are actually really hard to shield from. And when you shield yourself from them, you can have what's called a secondary, because the particle has to come through a material and it becomes something else. And those are equally as problematic. So people are, the physicists and the vehicle designers are always trying to understand, how do we get an optimal amount of shielding to protect the human and the equipment, because computers and boards in computers are actually susceptible to radiation damage as well. That how do we protect things without causing more of a problem downstream? So from a biology side, we look at the DNA damage in humans and try to understand what that means for their health. The galactic cosmic rays at the level at which station is in our atmosphere don't represent an immediate health impact, but we also surveil the astronauts for their lifetime, that they agree to say, do we think things are happening to you later in life because of the time you spent in space? That also helps us gauge kind of how you accrue damage and how your body repairs it. And we have a variety of scientists working on these areas for something like exploration missions, where they will be gone for 2 to 3 times the duration. And they'll be deeper into space and potentially be more vulnerable to the exposures. You mentioned isolation and confinement, and that is where we really try to understand a lot of the psychological stress that might go on. There are a lot of benefits in station that the crew talk about. There's a lot of public literature out there. There was an experiment called Journals by Dr. Jack Suster, where the crew members wrote about their experience. And those writings were taken and kind of broken down into categories, and a lot of metrics were done. But overall, the most positive experience crew members have is being able to see Earth from station and feel connected back to planet Earth. And so what you start to understand when they talk about these strong connections to Earth, and some of it has to do with, say, telephoning via satellite phone and having almost real-time access to another human being, is that with exploration, that's not going to be present. So then we try to understand, well, when those things aren't around, how much more of a stressor will the isolation of the future be? And we can kind of gauge percentages based on how the crew talk about them now. There's also the element of team. And Robyn just mentioned there are up to 7 crew on board, and that fluctuates depending on how vehicles bring people up and down. So they can go anywhere from 3 to 5 to 6 to 7, depending on the crew swap outs. But these people have to get along, and they have to work together and live together 24/7 for some period of time. A lot of that goes into training and setting expectations of what the mission is and how people experience life together before they even go. But some of it has to do with diversity. And the idea is we do have crew changeover now, that the crew move through station on different intervals. And in exploration, the 4 to 6 people you might be going with are going to be the 4 to 6 people you're going to be staying with for a while. So we also use station to understand the contribution of things like team dynamics, the diversity of the team, the changeover of the crew, to say if we could quantify those contributions when they're not present, what do we have to do with exploration mission, or how much differently do we have to prepare? Hostile enclosed environment actually speaks, and we probably should change the name, because I think the environmental control and life support people work really hard at making it not hostile. But the humans don't help themselves, because I mentioned exercise earlier as a countermeasure for the musculoskeletal system. Well, when you're exercising, you pump out a lot of CO2. So suddenly the equipment has to go from, say, some baseline level of CO2 of 6 people working and breathing, which may be kind of the amount we're producing now, watching the panel or talking on the panel. And then when your heart rate goes up to 160 beats per minute and you're breathing heavily, you're producing a lot of CO2. And now the system has to accommodate that and try to bring the CO2 down. And then I'm sure Robyn and Laura can very much speak to how the issues are of ventilation, because there's differences in how air flows in microgravity, and that's something we've learned on station a lot about. And the crew members might be locally experiencing a very different environment than what the global measurements might tell you. So we're actually trying to understand, again, that interaction between the ability to move air, ventilate, and then remove the CO2 when a crew member is doing something like breathe heavily due to exercise or hard work. And that actually is another lesson learned that we apply to extravehicular activities, where the human is in a very confined vehicle called an EVA suit. So it's been interesting to try to understand the dynamics of how much humans produce, how the vehicle or the system removes it, and can it keep up with the person, because the person's production could be highly variable depending on what you ask them to do. The other hazards that are out there have more to do with, I think, the concept of how do we meet the needs when you're essentially trying to take a planet with people. And it has to do with sensory issues like smell, feeling of things like a breeze or your feet in the grass, which are incredibly hard to replicate. And so far for station, we've been at durations of missions that haven't really approached having a problem with that, because people are going to come back to Earth and experience those things and they can't anticipate that time. But in the future exploration, you're going to have longer and longer stretches where you can't anticipate having those things you might really miss. And we're trying to understand how much you have to replicate those components versus when you can just allow the person to know that you will get it eventually. And so we try to understand, again, quantitatively as best you can, what it means to not have that sensory stimulation. But it's one of the areas the crew members also remark much about when they come back is, especially right now, you see them land in Kazakhstan, they open their helmets and they're like, there's nothing like the smell of the Earth. And I think our ability to grow vegetables and plants on orbit start to approximate that, but we haven't quite gotten there yet because we're not bringing soil. That comes with some other hazards and probably ecless challenges if we were to bring more particles. But if there's a way to combine the idea of feeding the crew by growing vegetables, contributing to something like oxygen production and CO2 removal, and then they also get texture, tastes, and smells that remind them of Earth, would be a huge countermeasure moving forward. And then it's just about sizing it properly and making it practical to do on something like exploration.
Yeah, that's what I was going to kind of chime in and say is we've, I think, developed very good countermeasures for the International Space Station, and we've learned about all these things, but now we're trying to refine those so that they work for, say, a mission to Mars. For example, on Space Station today, we have 3 big exercise devices, and that's a lot to carry on a trip to Mars. So can we develop an exercise system that is smaller but the same effectiveness for the human? Same thing with the food system. We fly 200 different menu items right now to the space station. The crew enjoys a wide variety of food. I mean, that's probably not going to be practical for a trip to Mars, and not all of those foods will survive, have the shelf stability to survive that kind of a trip. So it's going to be a more limited food system. Can we introduce variety through other means? Can we introduce variety through, as Jennifer mentioned, a supplemental crop system, right? That maybe won't have soil, it'll grow plants a different way. And then, you know, the ventilation we mentioned, we're working on our exploration ecosystem that Laura talked about. One of the goals we've got for ourselves is to try to lower the CO2 or increase the performance of that system so that the CO2 levels that the crew is experiencing are lower. And we're trying to understand what is that sweet spot, because when you try to do that, the equipment gets bigger, So it's a trade-off between designing the equipment for better performance and not being too big, right? So we're using the space station to evolve into what we think is a more Mars-like or long duration kind of mission-like system, and then understand that through testing it with the crew.
Great, thank you so much. And so we've talked a lot about the space station and about the environmental control systems on the space station. I would love to hear a little bit more about the challenges we're facing when it comes to life support systems and spacesuits even needed for deep space exploration.
And I can start this one. Imagine you were going on a round trip from New York to Los Angeles in a car. Imagine that car was the size of a human hair. That's what a Mars mission is. Imagine you've never taken that car, you've only ever tested it or driven it on a track inside a building. That's kind of what we're talking about if we only test these things on the ground, for example. So imagine you'd never experienced a hill or rain or a pothole, and you don't have any gas stations or service stations between there and back, right? And there's no hotels to stop. Everything you have with you is what you have, and your wits, and all of that. So the biggest challenge, I think, from a life support point of view, is the long duration and having to basically be your own mechanics and your own Mr. Fix-Its and Miss Fix-Its. So we're doing everything we can, like I said, to learn as much as we can about these systems now, so that we're smarter going forward, and we know what to bring as well. And Robyn mentioned, like, in situ manufacturing is a significant capability we probably need to create, so that we can fix a problem that we haven't anticipated along the way. And I think maybe Robyn can speak to the spacesuit challenges a bit. Spacesuits are basically small spacecrafts. They have their own thermal control and life support systems in them, so it's very similar type of challenges. And then, of course, they're going to have to deal with surface-related challenges when we start, having crew going out on the moon and Mars regularly. They're going to bring in all kinds of dust, which we're going to have to manage. So I would say they're very similar. And the good news is, on a surface, you have gravity, and we have gravity on Earth, so you can do some of those tests here on the ground. But the life support, we just have to do it on the space station.
And we just flew a piece of the new spacesuit, the spacesuit evaporator,
Right.
as a technology demonstration, and we're doing that right now on the space station. So that'll be part of our exploration suit. Building off what Laura said, when we first flew our ECLIS system for space station, we thought we understood it. Right? We thought we knew when this part would fail and how long this piece would last, and we were wrong in many cases. If we had tried to do a mission to Mars back then, we would have guessed wrong. We would have taken the wrong things. Too many of this, not enough of that, and we would not have had a successful mission. We would have had to take a lot more stuff, right? So what we've learned over the last 2 decades with our ECLIS system has actually reduced that uncertainty, and we can quantify that improvement in terms of spares mass now that we calculate we would need for our ECLIS system for a round trip to Mars. And we've been able to reduce uncertainty in terms of spares mass equivalent to several tons. And that's huge when you calculate just the weight of the stuff, and then the weight, and then the mass of propellant you need to push the stuff on a trip to Mars and back. It's a game changer for a mission to Mars. But we're not done yet. We think we can bring that down even more, and that's the reliability improvements that Laura talked about that we're making today to our systems. But we also need time. We need time on systems. So we've learned, we've reduced that uncertainty, but it took us a long time to get to that point. So now we're flying these evolutionary systems, and we need additional time on the space station to to gain the knowledge and be confident in those systems, so that we know when we do take that trip, we've packed the right stuff.
Thank you so much. So we've talked about life support system on the station a lot, and another part of the Artemis program, we want to put the first woman and the next man on the moon, but another part of that is Gateway. So can you tell us a little bit about Gateway and maybe what the life support system will look like there as well?
So for Gateway, we are working on the initial pieces now, and it'll be initially a limited, I would say, additional life support capability. We'll be flying Orion, so the crew will always have the Orion life support system to rely on while they're attached to Gateway. And then we'll be augmenting what's in Orion with additional capabilities on the Gateway, so that they can stay for longer stays. So we'll build it up. Initially, there'll be 30-day stays at Gateway, leading up to maybe 45, 60-day stays. Then our international partners are bringing an additional habitation module with additional ECLIS capabilities, our European and Japanese colleagues. And then ultimately, our plan is to bring a Mars habitat module to the Gateway, and that'll really have all of our long duration regenerative life support systems that we're flying to the International Space Station today and testing on the International Space Station. That's where all that stuff will be, and we'll practice again at the Gateway with our full up system there.
So the International Space Station is truly a global collaboration. We talked about, we've had, over 240 people from 19 countries and thousands of researchers who have contributed to the work that's been done on station. So how has working with these other countries to keep the space station operational for 20 years with humans aboard informed our plan for working with international partners on the Artemis missions?
Well, it says we can't do it alone, right? We've relied on this partnership, which is amazing, to do what we've done on the International Space Station and still do. I think even when our countries don't get along necessarily on Earth very well, we get along very well in the International Space Station program. And that's an incredible thing to say. And we're taking that partnership with us and building on it to do these missions beyond low Earth orbit together, because we know that we need contributions from everybody. Nobody can do this alone. It's too massive, it's too expensive. And our international partners want to be with us on this journey. They really want to contribute, and they're excited about contributing. So we're extending what we learned on station now to Artemis and signing agreements, and really looking forward. Everybody's starting to work on their parts, and really looking forward to those milestones.
Yeah, great point. I totally agree. We cannot do it alone. We are our best when we work together. So I would love to hear from each of you what you think human spaceflight will look like 20 years from now.
I'm going to let Jennifer start.
20 years from now, 2 decades. It seems so far away, but in 20 years, I'll be like, wasn't that yesterday? When did this happen? I completely agree that it will continue to be an international collaboration. I definitely see a sustained lunar orbit and lunar surface presence. That is going to be our next big learning opportunity to safely go to Mars. We are surprised every time at what, it's the I don't know what I don't know, gets you. And you really have to engage, right? This is why everything we've learned on Earth in terms of exploration said, you have to go and fail, and hopefully fail safely in terms of you anticipated it, and you learn from it. We have lots of ways to recover from the good type of failure right now. We can put ourselves in a low risk posture to take those chances. And I think the lunar opportunities in the next 2 decades are really going to put us in a position to do Mars well. I think the capability of the human functioning and performing in lunar orbit and lunar surface activities is only going to be improved. You know, you mentioned the suit, and there's a lot that has evolved about the suit with respect to how the human functions. It is another vehicle, but it's as close to you as your skin, right? And it also, we've learned a lot about how it needs to move with you and not against you. It shouldn't be more work. You know, we're humans, we use tools to help us. And the suit essentially becomes an extension, like exoskeleton-like. The other ideas of being a good partner, going back to human system integration. One of the things that kind of got touched on, I didn't mention as a countermeasure, because I really run a program that's designed not to rely on something like pharmaceuticals. And not because there's anything wrong, we're going to have them to some extent, but because the idea is when you metabolize a pharmaceutical or a food, it goes into your urine or your waste and then has to be processed. And when you're recycling water, you have to pay attention to that full life cycle. So we want to stick with things that are the least burden on the other systems and them know and anticipate what the human's expected to do. The other element is that we're going to continue to increase the diversity of the people who go, right? The idea of who is capable and what they're capable of. I think we continually make sure to remind people that there really are no limits. Our jobs are to help facilitate almost anybody to go. It's about what skill you bring to the table, what uniqueness you bring to the table. And we have only added value by adding to the diversity of the people who go and their perspectives and their expertise. So I just see more women and increasing number of countries, representatives from all kinds of countries being capable of flying with us and adding value to the missions of the future. No, I think that, thanks for the opportunity for the question, because it's good to step back and think about the future like that instead of the next 5 years.
Laura, what do you see in 20 years?
I am really hoping that we are on our way to Mars in 20 years. I'm hoping we've had a couple of missions by then, and learned all kinds of things along the way. But I agree. I think the moon is a good stepping stone and an area to go further away, where it's still not so far that we can't learn those lessons and still relatively easily recover. So I guess that's my vision. That's probably as far as my career will go. So I'm really hoping by then we've got people doing the Mars round trip.
And you'll still be at NASA. I probably will be retired by then. But I hope we're on Mars too. I would just add, don't forget about Leo as we go farther. I think as the administration, their policy, our policy, congressional policy, I think we're all in agreement, is we have to maintain a presence in low Earth orbit too, even as we go further. The trick is, how do we do that efficiently? So it makes me sad to say this, but one day we'll have to retire the ISS. And but we want to transition to something, right? We want to transition to commercial platforms in low Earth orbit, where we're buying what we, NASA, need. Other countries can buy what they need. There's commercial activity. We're all in it together. And so that's what I picture for Leo in the next 20 years. It's hard to pick a timetable because development of commercial capabilities is, it's hard to predict. But we're trying to do all we can to enable that future and keep ISS going, so we don't have a gap when the time comes to transition. So I really see and hope for that commercial partnership, both in Leo and in our efforts beyond Leo, as well as our international partnership.
Yeah, that's great. Thank you so much. I'm glad you brought up Leo, low Earth orbit, and that is a sad thought, the day we might have to say goodbye to the space station. But this conversation has just shown the ways that it's contributed to, our future exploration and just some of those facets. And of course, the whole time the International Space Station has really been benefiting everyone on Earth as well. So before we wrap things up, I wanted to give everyone an opportunity if you have any more thoughts or comments that you wanted to share before we end it up today.
I don't really have any. I just appreciate the opportunity. I've loved doing this celebration of our 20th anniversary and thinking about everything the space station has brought us. It's been my whole career pretty much, so it's near and dear to my heart. I intend to keep working on it and I really, really want us to fulfill all the potential we can out of this amazing platform in all areas. So I think we're really doing that, and excited to share that with everybody who might be watching.
I couldn't agree more. I also liked what Dr. Fogarty said about the diversity of crew. I think also on the ground, all the folks that support NASA, you'll notice a huge insurgence of women in the technical fields. In fact, this is an all-female panel, for example, today. And I think that's really increased the diversity of thinking, you know, and the way we're able to achieve things. In fact, my boss is a woman, and you know, Robyn's one of my bosses. And anyway, I'm just very privileged to have some very strong ladies in the field. So it's a great thing. Thank you.
Yeah, I agree with everything that's been said. And you know, working for the space program, it is an amazing opportunity to be part of the present and the future. It's also, as a woman and coming up through STEM fields and some male-dominated fields, you're like, if I can be there to be an advocate and help demonstrate what it looks like to do the role and do the job and be successful, and nobody even notices anymore, you know, because you are seamlessly accepted as part of this, as part of the team, and you bring solutions and you bring value. Incredibly proud of being part of the International Space Station. That has been present my whole career. I started after 2000. It was remarkable to see it evolve, and the way the facility operates today, and how we continue to use it as a test bed. And I agree with Robyn, it will continue to be a workhorse for us from all kinds of learning opportunities, science, tech demonstration. It only gets harder to go further away, right? And you want to have a lot of confidence and certainty and buy down certain risks before you move to the next step. So I think it's really set up quite an elegant way for us to move forward and have a test bed. You know, Laura talked about we can try to do things on the ground, but it's still going to leave some open questions about will it work in space. You've got to go into the operational realm to really put it through its paces, but you don't want to put humans at risk and the mission at risk for it, right? It becomes the job is to go test things and not switch yet, you know, to the next. People say, well, why aren't you doing the cutting edge? I was like, well, cutting edge is risky. And, you know, Robyn mentioned the word reliable. You don't know it's reliable. You need time. Some things are just about runtime on it. So it's an invaluable resource that'll continue to function in that capacity. I think engaging in commercialization is an amazing opportunity, and people that see value in it and be part of understanding what commercialization could mean. But it's been a privilege to work in the arena and to be part of having colleagues, you know, that are just stellar. We're not here for any other reason than to enable the future. So it's really a privilege. And I thank you for being on the panel. It was really great to hear from my colleagues.
Yes, thank you all so much. It was an honor to speak with all of you. And I know it's just so exciting to reflect on the past 20 years and ultimately exciting to look forward to what's coming next for the International Space Station and as we journey further into the solar system. So thank you again, everyone, for joining us. And thank you to everyone who watched. And we will see you next time.